Okay, so happy New Year to everybody. So we have 5 more weeks class, and there are still 2 main topics which I want to cover in the next weeks. And the first one, which we start today, are random matrices and the connection to freeness. And then we also want to see applications of freeness to von Neumann algebras. Von Neumann algebras were really from where the theory started, and where Roland introduced the notion of freeness. And random matrices somehow is a very surprising connection, this free probability theory. Also, when Roland created the subject, there was no relation at all with random matrices. He was motivated by the situation which one has in the group algebra of groups, with respect to free product of subgroups, or the von Neumann algebra version of this. Okay. And so in the beginning he just had this abstract notion. He did a free central limit theorem. He looked on the problem of having a free convolution and described this with the R transform. And at the beginning it was really not clear that this is of any use for von Neumann algebras. But then maybe 5 or 6, 7 years after he introduced the subject, he discovered that actually freeness also shows up in the random matrix world. This was quite a surprising thing. There was no indication before that this would happen. And this connection then really had a great impact. First of all, it made the connection of freeness with much more applied world, and random matrices is a much more applied subject, which has many connections to many different subjects. And so, tools in free probability theory can be applied to random matrices. Right? So we will see something like this. Okay, but this relation to random matrices also had a big impact on von Neumann algebras. It really gave some new results for von Neumann algebras. And that's what we want to talk in the last topic of this class. Okay, but now we should look on random matrices. Okay. And actually, of course, why is one tempted to have the idea that random matrices have anything to do with free probability theory? And the reason is that actually the most important distribution in free probability theory, namely the semicircle distribution, which appears in the limit of the free central limit theorem, this actually had shown up before in random matrix theory. So namely, it is also the most basic distribution in random matrix theory. Right? So this gave the idea that there might be some connection between the 2 subjects. Right? One has to follow this further. Okay, so let us look on this first on this occurrence of the semicircle in the random matrix world, and then see whether one has generalizations of this, which also include freeness itself. So our chapter now is on random matrices, and actually about the most basic ensemble of random matrices, which are the Gaussian random matrices. And then we also want to see that freeness shows up in this world, at least in asymptotic regime. So random matrices are n by n matrices, and asymptotics there means that I'm setting n to infinity, and then in this limit one sees the nice structure. Good. Okay, so let me define right away what do I mean in the random matrix, just in general. So what is a random matrix? Of course, a random matrix is a matrix, let's say n by n matrix, where the entries are classical random variables. Of course, we want to put this into our frame, so we put this into a star probability space. So our star probability space, and this is the one of, let's say, n times n random matrices. What is this? So it is given. So a star probability space, in our sense, needs an algebra, or it's actually a star algebra, and a stalemate. Okay, so what is our algebra? Our algebra is an algebra of n by n matrices, where the entries are coming from a classical probability space. So These are n by n matrices over a classical probability space. And of course, a classical probability space we have to rewrite in algebraic version. So it's an L infinity space. It's a random variables, but actually L infinity would be bounded random variables. And in general, we want also to include those which are not necessarily bounded. But of course, we need all moments. So I denote this by L infinity minus omega p. This is the intersection of all LP spaces. I will write this down soon. Okay, so this is the star algebra, and then the state on this. So this is the same as the tensor product of the ordinary matrices with this space, and my state is the trace on the matrices and the expectation on this. So it's a trace and the expectation, which as usually I will often do. Okay, so where? So what is this L infinity minus? L infinity minus omega p. Also omega p is just a classical probability space. A set is a probability measure on some sigma algebra. This L infinity space, this is our algebra of random variables, and there are those random variables which have all moments. So it's intersection of all LP spaces, but excluding infinity of the LP spaces omega p. And then, of course, you should check that this is an algebra. If you multiply two such functions, it's again there. Of course, the LP spaces are not algebras. Only L infinity is an algebra. Okay, but here if you multiply two functions, two LP functions, you will land in some other. Okay. Okay, so those are this. Then Mn of some algebra, let's say, A is here is L infinity minus. These, of course, those are the matrices where the entries are coming from this algebra, and of course I multiply them in the way that I multiply them like matrices, but for the entries I use the multiplication of A, and of course this is isomorphic to the ordinary matrices tensor A. Also, this is isomorphic to the usual matrices over C tensor A. But these are the n times n matrices. With entries from A. And A is just here this infinity space. Okay, then of course, so I'm taking on this, I'm taking my state, which is given by taking T little trace here, and the expectation here. So this E is just the ordinary expectation with respect to my probability measure. This is the expectation P, also this means the expectation of some random variable x in this space. So this is a function of omega and p. This is the integral of x omega and p omega. And the little tr, that's the trace of the matrices, but it's a normalized trace, because our linear functionals have to be unital. So this means the trace of the unit matrix has to be 1. The ordinary trace, where I just sum over the diagonal, is of course n, so I have to divide it by n. So this is usual trace, rescaled by 1 over n. This is normalized trace on n times n matrices. Good. Okay, so that's the abstract definition. And what does this mean? So what is now a random matrix, or what are our random variables, our non-conventional random variables in this setting? They are elements in this space. So this means our random variables are of the form, they are a matrix, n by n matrix, but the entries are coming from this L infinity space. So they are a matrix, the entries are denoted by Aij. Aij is running from 1 up to n. And of course, those guys here, they are just classical random variables in those at infinity minus space. So this means they have one moments. With A and J is at infinity minus omega k. Okay, and so what I'm interested in, the distribution of such a random variable, of such a random matrix, is now given by applying our state phi to it. The moments are with respect to phi, and so what does this mean? If I apply phi to such a random matrix, and this means I'm taking the expectation tangent trace, and this means the same as taking the expectation of the trace of A. So A is a matrix, of this I can take the trace, which is the normalized sum over the diagonals, then I get a random variable, and of this I can take the expectation. So this is then, so this is normalized trace, 1 over n. Here I'm summing over the diagonal, I also take the expectation. So that's what it concretely means to calculate moments of phi to this random matrix. Good. Okay, so that's a very general setting, and of course, to give some more, put some more flesh into this, I mean I have to specify the distribution of the entries. So this is so general that there's not much to say about this. Of course, we will look at various, especially Gaussian random matrices, where we specify the distribution of the entries of the random matrix. Here it's just arbitrary. It can be any joint distribution of the entries. Okay, but before going to this, maybe maybe one remark about why am I using the trace here? The trace for the matrices. Why is this? Maybe, of course, this is a canonical nice state on this algebra, and of course one would have to check that this is a star algebra. Of course, the star operation should be clear, and that this is really a state. So one has a positivity. So I mean, there are small details which one has to check, but this is okay. So this really is a star probability space. And why is the trace here a good object, and what does it mean to calculate moments with respect to the trace? I mean, if I have a matrix, then usually what I'm interested in are the eigenvalues of the matrix. And that is exactly what the trace is telling me. First, make this remark. Okay. I mean, this is independent of the expectation, so let us just take just an ordinary matrix and calculate moments with respect to the trace of it, and let's see what this has to do with the eigenvalues. So let's say we consider, let's say, self-adjoint matrix, because otherwise eigenvalues are a bit tricky. This is a matrix, and as if we take star, which is just an ordinary matrix, no randomness, just n by n matrix. Okay, so this is a self-adjoint matrix, n by n, so it has n eigenvalues, counted with multiplicity, that we call them lambda 1 up to lambda n. So lambda 1 up to lambda n. Eigenvalues. Okay. Of course, I count them with multiplicity. Okay, and then of course, we know that by unitary transformation, we can diagonalize A such that the eigenvalues are on the diagonal. So then we can diagonalize A via the unitary matrix, let's say U. In the form, I can write A as U D U star, where D is now a diagonal matrix which contains the eigenvalues in the diagonal. And U, of course, contains the eigenvectors. E is lambda 1, lambda 2, up to lambda n, diagonal matrix. Good. Okay, now the question is, so what are now the moments of A with respect to this normalized trace. So, and we can calculate, we can connect this of course with the eigenvalues by this diagonalization. So hence moments of this matrix A with respect to normalized trace are given by what? So what it calculating moments means I apply my state with power, let's say a to the m. That's the nth moment. And so what is this? Just okay, by diagonalizing it, of course A is the same as u star e power m. Okay, now of course, so I'm multiplying u d u star m times, and then of course in the middle, the u star will meet u from the next guy, because u is unitary, u star times u is equal to 1. So this means all the u stars between the d's are going away, and I'm left is the trace of the first u, and then of course I have d's multiplied m times, I have d to the m, and I have u star. Good. Okay, but now also this u and u star go away because the trace has the property that I can move an element from here to here, and then u star times u is also 1. So also because of the traciality of my trace, this u goes away, and this is nothing else than the trace of d to the m. Good. But the trace of d to the m is very simple to calculate. I mean, d is this one. If I take d to the m, this means I just multiply and take the power m of each of the entries here, and if I take the trace, I'm summing over this. And the trace is the normalized trace, so I'm also scaling this by 1 over n, and then I have here 1 to the m plus and so on, lambda n. Lambda n to the m. Okay, but this is now really the moment of a probability measure. So I mean, we know, I mean, if I have a star probability space, then the moments of our self-adjoint random variables can be identified with a probability measure on R, and from this we see exactly what this is. Namely, this is nothing but a probability measure which puts mass 1 over n on each of the eigenvalues. So this here is the same. Integral over R t to the m with respect to this distribution of A, which is a probability measure, and this probability measure is exactly the measure which puts mass 1 over n on each of the eigenvalues. So it's delta lambda 1 and so on, delta lambda n. So this is the so this is the probability measure. Mass 1 over n on lambda 1, mass 1 over n on lambda 2, and so on. Okay. And of course, this is now really the object you're really interested if you're talking about matrices or particular random matrices, namely you want to understand the eigenvalues of those guys. And this here is the canonical object which encodes the information about the eigenvalues. So this is the eigenvalue distribution. For deterministic matrix, and of course if I have a random matrix, then the same is true for averaging over things. Then calculating trace tensor expectation of our random matrix corresponds to the average eigenvalue distribution of A. So in the same way, the distribution of the self-adjoint random matrices with respect to our state, in this case, which is with respect to trace and expectation, is the averaged eigenvalue. Okay, so this means calculating moments of such random matrices with respect to the trace tensor expectation really tells us something about the eigenvalue distribution of the random matrices. And that's really what one wants to understand. Okay, so this was general about random matrices, but now if we want to make more precise statements, we have to specify, of course, the class of random matrices which we consider. I mean, this here is like talking about a classical probability space, or also non-commutative probability space. This is just an algebra of something. Okay, that's more or less all you can say about it. But then, to make things interesting, you have to specify something. So this means we have to specify the distribution of the entries of my matrix. I have to give you the joint distribution of the entries, and then I have a specific random matrix ensemble, and then maybe I can make interesting statements about this. Okay, and the most interesting, let's say the nicest ensemble of random matrices are the Gaussian random matrices, where the entries are actually given by independent Gaussian classical Gaussian, of course. Okay, so what we will consider are entries independent Gaussian random variables. Okay, and of course we want several joint random matrices. I mean, I'm only talking about several joint random matrices because only then I have an eigenvalue distribution. Because otherwise I might not have eigenvalues, or it's not so clear. Okay, so I'm talking about several joint random matrices, which means not all the entries can be independent. Because what I have above the diagonal in my random matrix must be the conjugate of what I have below. So this means I can only have independence of the entries, let's say, for everything which is above the diagonal. Okay, but for this I will take independent Gaussian random matrices, random variables, and if you want to calculate the moments of our random matrix, this means, of course, that we should reduce this, or we will reduce this, to the moments of the entries. So what we should understand is how to calculate moments of the entries, of the entries of our random matrix, and if the entries are Gaussian, then we should understand how do we calculate moments of Gaussian random variables. And of course, in principle, we know this. In particular, I only have one Gaussian random matrix, because this is exactly what we saw in our central limit theorem. How do we describe the moments of a Gaussian, classical Gaussian distribution? What do we call this? So this was in 2.7, where we did the classical central limit theorem. There we saw that the moments of the classical Gaussian or normal random variable x, this is a Saarland variable. Let's say we consider one of variance 1. Those are given by counting nice combinatorial objects, namely pairings. So the expectation of x to the m for Gaussian random variable. Of course, we have a distribution. You can write the normal density and you can do the integration. But more important from our point of view was that those guys are counting something, and they are counting the number of pairings of m elements. Which of course is easy to write down. This is n minus 1 times n minus 3 and so on. But it's counting those guys. Maybe it's even more appropriate to write this and actually be a summing over all the pairings, and each of them makes a contribution 1. Okay, so that's the moments of the Gaussian random variable. But now, of course, in our random matrix, we do not only have one Gaussian random variable, but we have several of them. and they are independent. So we should also have a nice convenient formula for calculating the moments of a product of Gaussian random variables where maybe some of them are the same and some of them are independent. Okay, and this is also very easy to do if we have this. So let us consider now independent Gaussians, and of course I'm here classically independent. At the moment there's no freeness, right? I mean, the point is, in this random matrix business, the entries are classical objects, and the freeness appears in the end somehow, because of the matrix structure. It's not like in the free-centered limit theorem, where at the very beginning we put in freeness as an assumption for our guys. But here we are really doing something in the classical world, but putting things in the matrix, and then somehow freeness will appear somehow in the final statement. It's not put in as an assumption. So we are dealing with classically independent Gaussian random variables. Let's say x1, x2, up to xr. So r of them. So I mean, each of them is Gaussian and they are independent. And so then, how do we calculate the joint moments in them? Moments are, so what is a joint moment? I have to take the expectation of any product in them. M's moment is I'm multiplying m of them. Okay, but I mean for any choice of indices, so let's say I take x and m, xi1, x2, up to x and m. I'm multiplying m of them, but for any choice of indices, and I want to see what is this moment. And I want to see this in a form, of course I know in principle, if I know precisely what the i's are, I can write it down precisely, but I want to have it in a form which is true for all choices of the indices. Because I mean, later when we calculate moments of our random matrices, we have to sum all possibilities for all choices of indices. So we would need a formula which is somehow uniform in the i's. Okay, but to see this, let us first, so what is this? I mean, of course, so I mean, the x's here, some of the x's are x1, some of the x's are x2, and so on. So what I have here is, of course, the product of x1 to some power m1, x2 to some power m2, up to xr to some power mr, where the m's is just how many of the i's are equal to 1. So m1 is how many are equal to 1, and 2 is how many of the i's are equal to 2, and so on. So mk is the number of indices, s's, and I of s is equal to k. Okay, and then so I have now a product of powers of independent random variables, x1 up to xr independent, and then of course the classical independence rule is very simple. It just says that such an expectation factorizes. So this is just expectation of x1 to the m1 times the expectation of x2 to the m2 and so on, times the expectation of xr to the mr. Well, because we're in a classical world, I mean, because I can commute here things, I can first collect all the x1s, then I can collect all the x2s and so on, and then I can factorize. Okay, and of course for each of them, this is not just a moment of a Gauss variable, and I know what this is. So I could write down this is m1 minus 1 times m1 minus 3 and so on, but this is not very useful. But this combinatorial description is much better because this tells me for this moment I should count the number of pairings of m1 points. Here I should count the number of pairings of m2 points, and I'm just multiplying this. Okay, but what this means is essentially that I'm summing over pairings now of all those points, but this here tells me that here I get the pairings where I look on the pairings between the x1s. Here I get the pairings between the x2s and so on. This means such a pairing for the x1s, for the x2s and so on. Together gives me the pairing for the whole sequence here. but I'm only allowed to pair x1 with x1, pair x2 with x2, and so on. So this means I'm summing here, effectively, over all pairings of my endpoints. But this factorization here tells me that I don't get pairings which connect an x1 with an x2. So this means I get a contribution of one pairing, but only if this pairing is really less than the kernel of I. And this means I should only connect x's for which the eigenindex is the same. I only should connect x1 with x1 and only x2 with x2 and so on. And each of them really gives me a contribution 1. Okay, and this is a formula which still contains the I in some sense, and one can even do this better because I can get rid over this by saying, okay, instead of just summing over the ones which satisfy this, and each of them has to weight 1, I just sum over all pairings, and the one which satisfy this have to weight 1, and the others have to weight 0. Oh, okay, this I can write in this form, so I'm summing now over all pi here, but then I have here a weight, and this weight should check whether I'm really connecting only the same variables, or whether I also do something forbidden, namely connect an x3 with an x7, and then I should get 0. But this I can do, okay, I have to look on each pair, so this means I have to take the product of the pairs of my pairing, and for each pair I should check whether it connects the variable with itself or with another variable, and this actually I can check by looking on the second moment between the two variables which are involved. So I can check by looking on the expectation of x, the variable at the position r, and the variable at the position s. Those are the two variables which are connected by this pair. This connects the variable at position r and the variable at position s. The variable at position r is xir, the variable at position s is xis. And now I'm taking the expectation of this, and of course this gives me exactly 0 or 1, whether I do something which is allowed or whether something which is forbidden. So maybe this here is exactly 1 if those guys are the same, because then I just have the expectation of, let's say, x1 squared, and I have normalized my variance to 1. The mean of all my variables is 0, and the variance is 1. So if this is the same, if IR is equal to IS, then I get 1. If it's different, then I have here two variables which are independent, and then this factorizes into the expectation of this times the expectation of this, but the expectation of my variables is 0. So this is 0 if IR is not IS. So this means this gives me a nice way without really maybe checking what pi is actually doing, writing it just in terms of my random variables, whether I have here pairing which is allowed or not. Good. Okay, so I get this formula which expresses somehow the higher moments in terms of the second moments of my variables. Good, and this is a very important formula which is the basis of what we are doing in the following. And actually, this formula is now not only true for independent Gaussian random variables, but this formula is linear in those guys here. And this means I can also take linear combinations of my variables, and for them I have then the same formula. So instead of looking just on independent Gaussian variables, I can also take linear combinations of them. And for them I have the same formula for calculating the higher ones. And then it might be that this here is not just 0 and 1, but it might be also something else. And then I get something which is called a Gaussian family. Which in principle is given by taking linear combinations of independent Gaussians. These arbitrary coefficients. Good. Okay, so let's write this down. So again, this formula. Let me write it down again. So important. So this formula says that the expectation of xi1, xim, so some moment, the higher moment of my variables is given by summing over pairings of m elements. And this means in particular, if m is odd, then there are no pairings, then this means they are 0. So this means odd moments are all 0, and even ones are given by summing over pairings, and then each pairing makes a contribution where I take the product according to the blocks of pi, and then each block gives me a contribution in terms of the second moment of my variables, where I take the second moment of x at the position r times x at the position s. Okay. And of course this formula is very, this looks like moment cumulant formulas. I mean, in the free world we would have a formula where we are summing over non-positive pairings, and then this is essentially the classical analog of this. Good, but anyhow, so I mean, this formula expresses moments of my variables x1, xr in terms of the second moments, in terms of second moments. And these second moments, of course, is usually called the covariance matrix of my variables. I mean, it's all the moments xi times xj, all possibilities. The second moment is not just one moment, but because it's all possibilities for the second moments, which is essentially the covariance matrix. And I mean, I derived it here for the situation that the x's are independent Gaussians. But because of the multilinear or linear structure of this formula, in all of the x's, so here on this side, this formula on this side is linear in each of the x's appearing here. So if I replace an x here by a linear combination of some x's, the same will happen on this side. So the structure of the formula will remain the same. So this means this formula also remains true if I take linear combinations of independent Gaussians. Since this formula is linear, its arguments, it remains true if we replace x1 up to xr by linear combinations of them. Okay, if I look on such linear combinations, then I get something which one usually calls a Gaussian family. So this is more general than just independent Gaussians. I mean, for independent Gaussians, the covariance matrix is essentially diagonal. It says, I mean, this here is 1 if they are the same and 0 otherwise. Okay, for a general Gaussian family, I can prescribe more or less an arbitrary covariance matrix. Yeah. Okay. Then this yields it's called the Gaussian family. And this formula tells me how to calculate moments of them in terms of the second moments. The second moments are somehow they are described by the covariance matrix. That's the input which I have to know about my Gaussian family, but then the rest is determined by this formula. Okay, this formula is very important, and it's usually called the Wick formula. So this here is the Gaussian family, and this formula, star here, is called the Wick formula. Okay, this is after physicist Wick, who did this in 1950 in the context of quantum field theory. But actually, I mean, it turns out that in mathematics and statistics, this formula, of course, was known much before. So, I mean, in statistics, there's a paper of somebody called Isserlis. This goes back to 1980. Also, quite important. Okay. But nevertheless, I mean, it was rediscovered in this context, and usually it's very important and used in physics, so usually it's still called big formula. Okay. And so now what we want to do, we want to take our Gaussian random variables and put them into our matrix. And actually, I talked here about real Gaussian variables, but actually we want to take now complex Gaussians because they have even nicer symmetries than the real ones. So the Gaussian random matrices I'm going to talk about are complex ones. But this is okay. I mean, I can also take in this Gaussian family, I can take complex combinations of Gaussian ones. And so I take a complex Gaussian, and this is given by a complex random variable where the real part and the imaginary part, each of them are real Gaussians, and they are both independent of each other. And then this is then also a Gaussian family, and I just have to specify or describe them by the second moments. We will actually take complex Gaussians. We will as entries of our random matrix, entries for our random matrix, complex Gaussians. Those are the form, okay, so I call it set, and this is x plus iy, form as square root of 2. No? So where x and y are real Gaussians and they are independent. Independent, real, random variables. Okay, so this is just again, this is a linear combination of independent guys. So if I want to calculate moments of this, or even star moments, I mean, of course, the set bar is x minus iy. Oh, okay, of course, set is not Salvatron anymore, but it has a complex conjugate. So if I want to calculate moments in sets and set bars, then I mean the same formula is still true, and I only have to know what are the second moments of those guys. Okay, and of course, what is the second moment? And the second moment now is the second moment of set and set bar. So it's actually a 2 by 2 matrix. So I mean, I have the second moment of set squared, which is the same as the second moment of set bar squared. And what is this? So if I multiply this with itself, I get x squared. Or I mean, first I get 2 here. Then I get x squared. Okay, and then I also get y squared, but the I squared gives me minus 1, so I get minus even y squared. And I also get the mixed terms xy and yx, but the expectation of xy is 0. Not because they are independent, it factorizes, and each of them is centered. So you see the expectation of this guy is just this, and because x and y both are normalized, this variance 1, this cancels away. So actually this is equal to 0. So this second one is equal to 0, and the non-trivial one is of course if I take the expectation between set and set bar. Because then I get the here I get a plus, because now I multiply Iy with a minus Iy. Then I get a plus expectation of x squared. So each of them is 1, and now you see why I have chosen this 1 over 2, so that I also get here 1. And of course, z bar z is the same. Oh, okay, so you see this is a Gaussian family where the second moments are given by this. So this means I have to couple a set with a z bar. So if I calculate now moments in such a guy, or maybe even independent of such guys, I mean for the second, I'm summing over pairs, but for those pairs I have to couple a set with a z bar. A set with a set, or a set bar with a set with 0. Good, okay, so we will put such guys in our random matrices, and then the idea with random matrices is that they are getting really interesting if I'm sending n to infinity. N is the size of the matrix, n by n matrix. And for this I should choose a good scaling, because I should scale some of my matrix in such a way that for n equal to infinity it does not go to 0, it does not explode, but it has the right order. So I should choose the right scaling, and maybe to see what this should be, let us look at the second moment. So we will also do the scaling in n. In order to have a non-trivial limit, when n goes to infinity, we have some non-trivial limit. So I'm going to infinity, and to see what we should choose, let us look at the second moment. So namely, if I have, let's say, if I have a matrix where the entries are, let's say, Gaussian guys, so what is the trace of a squared? So what is this? This is 1 over n, and then I'm taking the sum ij from 1 up to n, the expectation of aij, so the entries of a are the aij's. So if I take a squared, I have to multiply my entries to get the a squared matrix, and then taking the trace means I'm summing over the diagonal. Okay, so this j here is matrix multiplication, the sum over j is matrix multiplication, the sum over I is taking the trace. And then of course I also take the expectation, and I get my scaling 1 over n. Okay, so if my guy is self-adjoint, then of course the AJI is the same as the AIJ bar. Okay, so now if my entries are Gaussian variables, then you see this is the z bar, which in my usual scaling is 1. Okay, but if this would be 1, so this is 1 for all ij, let's say, then I'm summing here over n squared of those guys. So I get here n squared, if I divide by n, I still have n. And of course this explodes at n goes to infinity. So what I should do is, this expectation here should not be 1 for each of the ij's, but it should be 1 over n. So this means this here should be of the order 1 over n. So we are not asking that our expectation of our entries is 1, but it should be 1 over n. Or just saying we are scaling things with 1 over square root. Okay, good. But now maybe after all these motivations, let me now define a Gaussian random matrix. So we will take a matrix where the entries are apart from the symmetry condition, which is given by the fact that the matrix should be self-adjoint. Given by independent complex Gaussian variables with the right scaling of the variables. Good, so here's the definition. So, a Gaussian random matrix, and all our random matrices are self-adjoint. So this is not saying self-adjoint, but they're always meaning self-adjoint. So Gaussian random matrix. So let's say this is an n by n matrix. Random matrix. A is equal to j. From 1 to n. And now I have to specify the distribution of the aij's. First of all, it should be self-adjoint. So A should be equal to n star, which means, of course, that the aij is equal to the aji bar. And such the entries, okay, the entries are essentially independent complex Gaussians apart from the symmetry condition, but the nicer way to formulate this is they form together a Gaussian family, and then I only have to specify the second moment. And of course this depends on the indices. So such that the entries in J are running from 1 to n. They form complex family. So it's a Gaussian family, and I have to specify the covariance, because I mean, for such a family I have this formula which gives me all moments in terms of the second moments. So specify covariance, and so this means I have to specify the covariance between any entry of my matrix and any other entry. So let's say the entry aij and the entry akn. Okay, so what is this? So we said we have to normalize it with 1 over n. So if it is not 0, it should be 1 over n. And then we have to specify when is it 0 and when not. Okay. What we want is actually that this variable, this variable should essentially be the same as this up to the symmetry condition, because otherwise those guys are independent. Okay, when can this be equal to this? This, and actually it also must be the complex conjugate. So this means KL should not be the same as IJ, because then I would have set, which is 0. What I want here is set and set bar. And the bar appears exactly at the position, at the mirror position. Also, this means if KL is the same as IJ, but the other way around, so this means if I is equal to L and J is equal to K, then this is the complex conjugate of this, and then the variance should be not 0. Otherwise, it should be always 0. This means what I want is that J is equal to K and I is equal to L. Because then this, in my matrix, is the complex conjugate. So this means this should be 1 over n if I is equal to L and if J is equal to K. And otherwise, it's always 0. So this is my prescription of the second moment. And this then specifies everything. Okay, so what I'm defining here is usually called GUE. And so we say, if I have such an A, then A is the GUE, and of course it depends on n. For each n I have something like this. So then I say A is GUE. Okay, this GUE, this stands for Gaussian unitary ensemble. This means Gaussian, this should be here, unitary ensemble. Okay, so usually ensembles are sets of matrices. Okay, whatever. The Gaussian is clear, unitary might not be so clear. I mean, I'm looking here on several choice matrices, not on unitary ones. So this unitary is not the nature of my matrix, but it's about the symmetry of the matrices. Because I mean, if I'm looking on such matrices, then this distribution of the entries is invariant under conjugations by unitary matrices. So this unitary tells me about the symmetry of this ensemble. Good. Okay. And so, let me make a few remarks. And maybe the first remark is that this here really specifies everything about the distribution of my entries. So, some remarks. First is that we have specified here everything. I mean, of course, because I have complex variables, I should not only specify the moments of the variables, but also moments where I have the adjoints. And of course, I mean, here it looks, here I'm not putting the adjoint here, but of course, because of the symmetry, the AKL is the adjoint of ALK, this is contained in this description. So note that we have Aij is actually Aj bar for 1 from 1 to n. Right? This is the case because I want a self-adjoint matrix. Well, this condition really, in terms of the entries, means this here. And this tells me, of course, that if I'm on a diagonal, then of course II is the same. On the diagonal, this is telling me that the guys on the diagonal must be real variables. And the guys not on the diagonal, I mean, they must be pairwise connected. I mean, Ij is the conjugate of Ji. So this means I have all the conjugates which are around, I have in this formula here. On the diagonal, I don't have conjugates, that's real, but otherwise, I mean, I have it contained here. So this means all star moments of second order in Aij. So this means all moments which contains Aij and they are joined, they are actually given by this formula. They are all contained here. Are given by our prescription of the covariance, but then the higher moments are given by the Wick formula in terms of the second moments. So actually I have specified all star moments of my interaction. The Wick formula star. Good. Okay, maybe another remark is, so here I said this is the nicest Gaussian ensemble. I'm taking complex entries. And we will see, I mean, this really gives a very nice formula for the calculator of the moments. But of course one could also say, okay, if I'm not taking complex entries, but just take independent real Gaussians for the entries, well, what is this? And I can also consider this. And this is then usually called the GOE. And there's also a complex work, quaternionic version of this. Okay. And for the semicircle, conversion to the semicircle, there is no difference. No? I mean, the result is the same. The calculations are a bit more complicated in the real and the quaternionic case. That's why we do the complex case, because there everything is very clean and nice. And I just want to point out that I can also consider real and quaternionic versions of this. So it also has what's called the GOE. So it goes Gaussian orthogonal ensemble, and there the entries are real. Real entries. The entries are real Gaussian ones. And this orthogonal is now again the symmetry for this kind of matrices. And one also has GSE, which is Gaussian symplectic. Ensemble where the entries are quaternary. Okay, but we will stay with the GOE. And now, let's see what we can now say about moments of a GOE matrix. Okay, I already gave you the idea that we should be able to calculate them quite precisely, and then if n goes to infinity, we should see the sinusoid. So let us do this. Maybe the theorem. First do the calculation for finite n, and actually this can be done very precisely, because we have this very nice description. The second moments, and then is the Wick formula of moments. Okay, so here's the statement. This is a theorem which usually goes under the name of Genus expansion for the GOE. Because we are writing moments in terms summing over terms which can be considered as related with some G's. For okay, so let's maybe n minus n, GOE matrix. State controlled by phi. This is traced into E. And then I want to calculate moments of my A with respect to this phi. So I should take power A to the M and calculate what is phi of A to the M. Yeah, we have a nice formula. Then we have for all powers M, which are numbers, that moment is given, and now we get a formula which is somehow similar to the Wick formula for Gauss variable. So namely we are summing over pairings of M. Okay, but we get weights for the pairings. Huh? It's not that all of them contribute 1, but we get a factor power of n, and the power depends on the pi. It's not the same for all pi. Maybe what I get here is n to some power, and this power is the number cycles in gamma pi minus 1 minus m over 2. Okay, this minus 1 and this minus m over 2 is here, but what is this? So actually here I'm counting the number of cycles. Okay, so I'm going over, pi is an element with a pairing, but I'm going over to the permutation group. Gamma is not a pairing, but gamma is an element in the permutation group, because I multiply things. Pairings I cannot multiply, but I can multiply permutations, and so I consider pi as permutation. So I identify where pi, which a priori is a pairing. I'm identifying this something which is also called pi in the permutation group. So this SM is the permutation group of n letters, permutation group. And I do this, a pairing consists of blocks, and now I'm just declaring those blocks as cycle of my permutation. A block is just, okay, a pair is just 2 elements, and cycle means I must have a mapping that I go from one element to the next. But for a pair, it is clear. The first element goes to the second goes to the first. So I'm declaring the block S of pi. So pi just only consists of blocks. I only have pairing. So any block, I now say this is a cycle. So this means there's a permutation. The pi sends now this R to S and this S to R. So pi of R is S, pi of S is equal to R. And I'm doing this for all pairs, so I really have now a permutation which tells me each element from 1 to m goes to some other element. So namely it goes to the other element which is sitting in the block of this element. Okay, so this means I can, this pi, pairing, I can also consider it as a permutation, and this gamma is now also a specific permutation, namely it is the long cycle which just shifts every element by one, modulo n. Cycle notation means 1 goes to 2, 2 goes to 3, and so on, and then m goes to 1. This of course means gamma of k is just k plus 1, but of course I'm counting modulo n. So from here I'm going back to 1. Okay, and then now what is this number here? Of course this is now the number of cycles. So this is now, this is a pairing, I multiply this with gamma, this again arbitrary permutation, and then I count the number of cycles. So this is what I use this here. So this is the number of sigma, this is the number of cycles of an element in my permutation group. Good. Okay, so that's the statement. Okay, so then let us prove this. Okay, and of course you see, that if n goes to infinity, we have to see what is this here. Some pairings will survive in the limit, others will disappear. It's clear, of course, what we say. Okay, but let us first prove this. And we just have to calculate the moments by going over to the entries of the matrix, and for the entry of the matrix we have a nice formula for calculating their mixed moments, the Wick formula. This should be enough, this is enough information for getting this result. Good, so we want to calculate the nth moment of A. Let's just do this. So what do we have? So I say phi A to the m. Okay, so what is phi? This is taking the trace and the expectation. So since I take the expectation of the trace of A to the m. Okay, now I should write down what this really means in terms of the entries. The trace means I'm summing over the diagonal of this matrix. And so what are the elements of this matrix on the diagonal? And they are given by multiplying this matrix. And so this is what? So this little trace is is normalized, so I have the 1 over n coming from here, and then, okay, I'm multiplying the entries here, and so matrix multiplication is given by summing over all the indices, so I have here I1 up to n, let's say, all running from 1 up to n, and then I have the expectation of I1, I2, I2, I3, and so on, up to I1. Okay, so I mean, to take the nth power of my matrix, so what is the I1 entry of this power? This is given by summing over all those guys. So the summation over I2, I3, and so on up to IM is just a matrix multiplication. And then the trace means I have to sum over the diagonal, which means I also sum over this and this. They are also the same. So if this is the same as this is the same as this, and this is the same as this. This comes from matrix multiplication, and that this is the same as this is taking the diagonal of this, and then summing over this is the trace. Okay, so that's what I have to calculate. And you see, I have to calculate, so those are now joined the moment of my entries, but I have to do this for all possible choices of the i's. And for this it is good to have a formula which is uniform in the i's. I don't want to care which of the i's are the same and which are not. Good, but I have the Wick formula, so for each choice of the i's, this is now given by summing over the pairings. I have here m terms, so this is summing over the pairings of m elements. And then, for each such pairing, I get a contribution in terms of the second moments, so I'm taking the product of all blocks, and for each block, I take the corresponding second moment. So I'm taking the product over all the blocks. Let's say I do a block at position R and position S, which connects R with S. And then the contribution of such a block is the expectation of the element at the position R. Okay, what is the element at the position R? This is an A. You see, this is position 1, position 2, position M. So you see the first guy here is the R. So this is R. And then the next is just one more. This is R plus 1. So the A variable sitting at the position R is A by R plus 1. And the variable sitting at the position S is A by S plus 1. Good. Okay. So this is the Wick formula, which reduces any moment to second moments. And for the second moments, we have to prescribe what they are by prescribing covariance. So this is this here. Okay. So those are 1 over n, and in the cases where this index is the same as this index, and this index is the same as this index, and they are 0 otherwise. So this here is 1 over n. But only, and in most cases it is 0, only in a case where this variable is the same as this, which means I of R must be the same as I of S plus 1. And this is equal to this, which means I of R plus 1 must be the same as I of S. And then it's 1 over n. Maybe now you see also where the gamma is coming from. I mean, the gamma makes a shift of the indices by 1, and you see what I'm doing here is, I mean, I have here R and S, and then I also have to consider R plus 1 and S plus 1. But those are just the gammas of this guy. So this means, this here is I of S plus 1. This is the same as I of, okay, I mean it's a shift of the S, but what is the S now? I can also write the S in terms of the R, because this is just pi of R. Okay, I take pi of R, and then I'm shifting. So it's gamma of this. So the PS, I mean, RS is a pair of pi, which means as a permutation, pi sends R to S and S to R. So this means this S here is nothing else than pi of R, and then I'm adding 1, and this is the effect of gamma. So this here is, this I of S plus 1 is the same as I of gamma pi of R. And here you see I have the same, but the other way around, in terms of S. Here I have I of gamma of pi of S. Pi sends S to R, and gamma gets 1. This 1, of course, is always to be understood in the sense of what. Good. So, what do we have here? So we have, first, let's collect the 1 over n terms. I mean, I have 1 over n here. And then for each pair of my pi, I get an additional 1 over n. Okay, I mean, of course, I have m over 2 pairs. If I have m elements, then I have m over 2 blocks, so I get 1 over n, I get this m over 2 pi's. So I have here 1 over, I have this 1 coming from the normalization of the trace, and I have this m over 2, that's a contribution of each second element. Good. But then, of course, I have to sum, and I have a big sum here, I have to sum over all indices, and I have to sum over all pi. And the summation over the indices is usually a problematic thing, because I'm summing up to n, and if n goes to infinity, I mean, this sum here is getting bigger and bigger with n. This is hard to control. This here is okay, this is a finite sum. And now the point is that I'm exchanging my two summations, and then I can do this summation in a very nice way. So instead of first summing over I and then over pi, I do the other way around. So I'm summing over pi, over pairing, and then for each fixed pairing, I'm summing over the i's, which is my index tuple, which of course we can also consider as a function from the set 1 to m to the set 1 to m. Before part of this identification. And so what I have here is now the product of delta contributions. So this tells me now whether I get the contribution 1 or 0. So it really means, I mean, if I'm fixing my pi, there are some tuples which makes a contribution and other tuples don't. And this delta here tells me exactly which contribute. And you see what is the condition? I mean, I have here a condition that I of R has to be I of something in R. And here I have I of S has to be I, the same thing in S. And I'm multiplying this over all pairs. So you see, I have exactly this condition here for the two elements in the pair. So this means in the end, if I multiply this, I have this condition for each element. So this means I have here S from 1 to m. Delta I of S has to be the same as I of gamma pi of S. Okay, so that's what I have here now. So what is this telling me? So this means I have to sum over the i's which satisfy this condition. But this condition, what does it tell me? That if I consider I as a function, then it tells me I at S has to be the same as I at gamma pi of S. Okay, but gamma pi of S is the next element in the orbit of S in this permutation gamma pi. So you see, if I'm now looking on the cycles of gamma pi, then this condition tells me on each cycle I must be constant. Because I mean, if S is in some cycle, then I can choose there any element for I of S, but then the I on the next element in the cycle must be the same. Then again, the next element must be the same. So this means on the cycle, the I is fixed. So this means I can choose for each cycle, I can choose a value of I, but then it must be the same on the whole cycle. But for different cycles, there's no condition. So this means, this here tells me that the function over which I sum here must satisfy exactly the property that it must be constant on orbits of gamma pi. The orbits are just the cycles. Yeah, but then this summation here is now very clear, because it tells me in this summation here I can choose one value, 1 up to n for each cycle. Okay, so what I get here is just n to the number of cycles of gamma pi. This is n to the number of cycles of gamma pi. Right, so you see, you really can do it in a very nice way, this very big summation here, because we can control it, this condition very easily. And now we are done. So now we are left with the summation of all pi, and we just collect our integrals. So this is the summation. Over pairings. Each pairing makes a contribution n to the number of gamma pi, and then I have also to take those into account, so I take -1 minus n over 2. And that's exactly what you can do. Okay, so maybe. So this is a nice formula, but of course it's also a complicated formula. If m is big, I mean there are many partitions, and I mean they make contributions which might not be so easy to control. And actually this is called a genus expansion, because you can interpret this as the genus of pi. It's somehow the genus of the surface where you can draw it without having intersections. Okay, but anyhow, I mean what we are interested in is to understand what happens if n goes to infinity. Maybe let us first look at an example of this formula, just to be sure that we understand what we are doing. Let's look on the fourth moment. Of course, the second moment is trivial, that doesn't say anything, but let's consider n equal to 4. So we have the fourth moment, and then we have to sum here over 3 terms. There are 4 pairings or 4 elements, so the pi's, the possible pi's, are 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. So those pi's, you can say those are pairings, but now we are reading those pairings as permutations. So this is permutation, which says 1 to 2, 2 to 1, 3 to 4, and 4 to 3. And then what we have to see, what is gamma pi in those cases. And then of course we have to calculate number in gamma pi -1 minus m over 2, m is 4, so we have to subtract here -3. That's the power of the density. Good, but let's see what is gamma pi in this case. So gamma pi is a permutation. So what happens with 1? 1, first we have to apply pi and then gamma. So 1 under pi goes to 2, and under gamma it goes to 3. And 1 goes to 3. What happens to 3? 3 goes to 4, and 4 goes to 1. So we are going back to 1, so this is one cycle. Okay, and what happens with 2? 2 goes to 1 under pi, and gamma sends this to 2. So this is a fixed point, cycle length 1. And then of course it's clear that 4 must also be a fixed point, so 4 goes to 3 and it goes back to 4, that's okay. Now and you see, so we have here 3 cycles, -3 gives 0. Which means we have here n to the 0, which means we have a contribution which is therefore all n. This is something which survives. Okay, then this guy here, what happens there? So 1 goes to 3, and under gamma it goes to 4. 1 goes to 4. 4 goes to 2, 2 goes to 3, 3 goes to 1, and 1 goes to 2, and now of course we have to come back. 2 goes to 4, 4 goes to 1. Okay, so you see here, the situation is different. We only have one cycle, so this guy here is -2. So we get here n -2, and this is something which is suppressed. Here, of course, here again, we have a situation like here, 1, 2, 4, and 3 cycles, contribution n to the 0. And so this means in the end, in this case, the fourth moment of A is given by 2, this and this is n to the 0, and then we have a contribution n to the -2. And of course it's clear, I mean, the two contributions which we have here are coming from non-crossing pairings. And that's of course what we expect, what is true. In general, we have here power 0. I mean, we never have something which is bigger than 0, because this would be a problem. No? Okay. But we have here power 0 exactly if we have a non-crossing pairing here. So this means in the limit, we exactly have, we are summing over the non-crossing pairings, and then they contribute with 1, and the rest disappears. And then of course we know those are the moments of the semicircle. Okay, so maybe let me formulate this as a proposition, which exactly tells this, that the leading order corresponds exactly to the non-crossing. Even, because otherwise there are no pairings. So for any pairing of elements, we have that this exponent in the sum can be at most 0. So the number of cycles, pi minus 1 minus 2 is always less or equal to 0. For all P2 and for all pairings. So which means if n goes to infinity, this guy does not explode. And it will exactly, I mean, it will suppress anything for which I have strict inequality here. And it will leave us in the end is the guys for which we have equality. And so the second part here is we have equality exactly if, only if, pi is a non-crossing pairing. Good. Okay, and the proof of this, so I just want to give quickly the main idea is that actually, we should see essentially a kind of recursive structure. I mean, because we know non-crossing pairings have a recursive structure, so it would be good to see here also the same kind of behavior. And for the permutations, for gamma pi, the point is that we are looking for a fixed point. So namely, if gamma pi has no fixed point, then it is clear right away that we are strictly less. Because if you have no fixed point, then the number of cycles cannot be more than m over 2. Because then each cycle must contain at least 2 elements, so there cannot be more than m over 2 cycles. Then the number of cycles, gamma pi, must be at most m over 2, but then the quantity which we have, namely gamma pi minus 1 minus m over 2, is then strictly less than 0. Because this here is at most m over 2, and then I'm subtracting another one, which means this is strictly less than 0. Which means if I don't have a fixed point in my gamma pi, then I have here something which is strictly less than 0. Okay. So this means I should really look at a situation where I have fixed points, and these fixed points really make the connection with the recursive structure of non-crossing pairings. Because if I have a fixed point, so if gamma pi has a fixed point, so what can we say then? I mean, then we know something about gamma pi, and this also means we know something about pi. So say we have a fixed point, let's say gamma pi of pi is equal to pi. So we have a point which is mapped to itself under this permutation. So and this tells us that pi of I must be, the guy, or so the gamma of pi of I must be I, so gamma shifts by 1, so this means that pi of I is just I minus 1. Because pi of I goes to something, and this something must under gamma go to I, and this is of course I minus 1. So this means pi is a pairing, that the pair which I have here corresponding to I is just I and I minus 1. And you see this is now a pair consisting of neighbors. Okay? Those are the pairs which I can take out. And a non-crossing pairing is determined by the fact that I can iterate this. And here I can do the same. So this means pi is, let's say, pi twiddle, and this pair I minus 1. So I have one pair which is this, and then I have the other pairs, which is now a non-crossing partition of m is a pairing of m minus 2 elements. And actually what we can now do is we remove this pair. And we should check what are we doing with the rest. So in this case, we remove this pair, so we remove I minus 1 and I, and then we get a new this is just the part of pi which is left after removing this one block. And we also get a new gamma twiddle, and a new gamma, which I call gamma twiddle, which is just what is left of gamma, and I have removed those 2 points. So this is now cycle 1, 2, and so on. And then I have I minus 2. This would go to I minus 1 and then to I, but those are not there anymore. So I go to I plus 1, which is the next one after this. So, okay, this is just what gamma, what is left of gamma after I'm removing those 2 points. Okay, and actually now one also sees that the quantity in which I'm interested is the same after this removal if I just replace m by m minus 2. So I can point this such that the number of elements in gamma twiddle, pi twiddle, minus 1 minus m minus 2 over 2. That's the quantity which corresponds to this, because those are guys which are only living on m minus 2. But this is the same as gamma pi minus 1 minus m over 2. And why is this? This is because I have what I have done in gamma twiddle, pi twiddle, I have removed one cycle. Namely, I have removed the cycle, this fixed point. I have removed this fixed point. And the rest, I also have removed the I minus 1, but this was part of a cycle which now only becomes smaller. I have not removed another cycle, but I just have made another cycle smaller. So I have really only removed one cycle, and this means that I have this equality. Okay, but this means if I want to check what this is, okay, if I have no fixed point, then I know it's strictly less than 0. If I have a fixed point, I can go over to this guy here and now ask the same question. If there is no fixed point here, then I know again this is smaller than 0, which means also this is smaller than 0. Okay. So this tells me in particular that, if I want to have something which is equal to 0, I must in each step, I must always find a fixed point. I start with removing a fixed point, and then I must find another fixed point and removing this. But this corresponds to the level of the pairings exactly that I always find a pair which consists of neighbors. And then I remove this, and then again I must find a pair which consists of neighbors. And then I'm going on, and this must happen until nothing is left. But this is exactly the definition of a non-crossing or a recursive characterization of a non-crossing pairing. So you see that, this recursive structure on this level here is encoded by fixed points. But this really corresponds exactly to a pair of neighboring elements. If I'm removing this, I'm just getting the smaller problem of the same type. Okay, so I think time is over, so I'm not writing down more details, but I think this is hopefully so maybe everybody should do it by himself. Good, okay, so I think that's it for today, and then of course next time we will write down that for n going to infinity we get the semicircle, but then the crucial point we need to see whether this is just an accident that we see the semicircle here, or whether there is really more in the random matrix world. free probability theory, the semicircle is of course an important thing there, but the crucial property is freeness. Also, what we should see is whether we also have freeness in the world. Okay, next time we will see that this is